Hey everybody, welcome to the first of many problem-solving videos that I'm going to do in the coming months on pre-calculus and calculus content. I'm also making videos on calculus lessons, though those take a lot longer to produce than these videos do. This video is mostly about linear equations and linear functions, though we'll also have some content about general functions and change, like proportionality, domain and range, and that kind of thing. The first problem is to determine the intercepts and slope of the line with this equation right here, 3x plus 4y plus 5 equals 0. That's a linear equation in x and y. You only see x and y to first powers and no trig functions, no exponential functions, nothing like that. Its graph will be a line. We also want to graph that line. All right, start with the intercepts. Those are the easiest things to find. For the x-intercept, what you want to do is you want to set y equal to 0 because you're trying to figure out where it crosses the x-axis. That's where y is 0. Set y equal to 0 and solve for x. Take this equation, replace y with 0. You'll get 3x plus 4 times 0 is 0 plus 5 equals 0. I then want to isolate x. I want to solve that for x. I can subtract 5 from both sides to get 3x equals negative 5. Then I can divide both sides by 3 to get x equals negative 5/3, negative 1.6 repeating. That will be the x-intercept. What about the y-intercept? You want to find where it crosses the vertical y-axis. That's where x equals 0. Set x equal to 0 and solve for y. So you get 3 times 0 is 0, plus 4y plus 5 equals 0. We want to solve that for y. Subtract 5 from both sides and get 4y is negative 5. Then divide both sides by 4 and get y is negative 5/4, and that would be negative 1.25. The next thing to do is to find the slope. That's going to be what we find when we get this equation in slope-intercept form, when we've solved for y as a function of x. So I need to look at that equation and say to myself, I have to isolate y. I need to get rid of the 5 and get rid of the 3x on the left side, and then also divide both sides by 4. So I can look at that and say, I'm going to subtract 3x from both sides and also subtract 5 from both sides. I can write 3x plus 4y plus 5 equals 0 implies 4y equals, after cancellation on the left, negative 3x minus 5. Then divide both sides by 4. I can write y is negative 3x minus 5 all divided by 4. When you divide the combination of two expressions like this by a single quantity, you can divide each of them by that quantity. So I get negative 3x over 4, which is the same as negative 3/4 x, and then a minus 5/4. Okay, so there is the equation of the line, y equals negative 3/4 x minus 5/4 in slope-intercept form. That quantity right there, that is the slope, negative 3/4. And this quantity, negative 5/4, is the y-intercept, which we've already found. So the slope is negative 3/4. That measures the steepness of the line. This line is going to be representing a decreasing function that goes down as x goes up. And it's change in y over change in x. So for every 4 units that x increases, the change in y is negative 3. Y would go down by 3 units. And that will help us graph the line. And that's the last thing to do here is graph the line. Let me make kind of a big graph here. And we'll do this carefully. So I'm going to mark off some tick marks on the x-axis like this. Try to make them as evenly spaced as I can. Say these are 1 unit apart. It's not possible to draw perfect graphs. You're just trying to draw pretty good graphs. Be good to label these as well. 1, 2, 3, etc. There. I'm not going to label all of them. Negative 1, negative 2, etc. Negative 3, negative 4, negative 5, 6, 7, negative 8 over here. 1, 2, 3, 4, etc. up there. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. All right, let's try to go ahead and make our graph. You can go ahead and draw the intercepts. X-intercept at negative 5/3. Again, that's negative 1.6 repeating, about negative 1.7. and the y-intercept at negative 5/4, which is negative 1.25. So negative 1.6 repeating, you might say, is right about there. That's the x-intercept. Negative 1.25 is right around here. That's the y-intercept. You know the graph's got to be a straight line. You could just connect these dots like this and get a pretty good graph of this line. Be good to use a straight edge or a ruler to make sure it looks straight. Not too bad for a freehand drawing here. If you wanted to add more to this, you certainly could. Remember that the slope is negative 3/4, change in y over change in x. So for example, if I let x increase from 0 to 4, y has to go down by 3. So if for example, I could draw a right triangle in here, about like this, that would represent, say, the change in x, that would be 4, and this would represent the change in y, and you'd think of it as a negative quantity because the function is decreasing here, y is going down. And so, for example, since this is negative 1.25 right there for the y-intercept, this point would have coordinates of x is 4 and y went down by 3 from negative 1.25. It would be down to negative 4.25. Is that accurate? No, it doesn't look super accurate because negative 4.25 would be about there, but you know, things are not going to be perfect. So pretty good for a fairly quick graph. The next problem has 3 parts to them. Let's take it step by step. Part A says find the slope-intercept form of the line passing through the following points: 5, negative 4 and negative 3, 8. Let's go ahead and do that first. The slope, also called m, as I said in problem number 1, is the change in y over the change in x. So I've got to figure out how much does y change and how much does x change. I could draw a picture, but let's just go ahead and use the formula right away. The formula for the change in y is y2 minus y1, or if you prefer, y1 minus y0, and the change in x is x2 minus x1. Now, some people are confused which point is which point has which labels. Point is, it doesn't matter. As long as the x coordinates of these 2 points are different, you can use this formula as long as you stay consistent. We might as well take them in the order that they're given. x1, y1 will be this point, and x2, y2 will be this point over here. So we'll get y2 minus y1 will be 8 minus negative 4. You got to be really careful about signs. And x2 minus x1 will be negative 3 minus 5. Of course, subtracting a negative number is the same as adding a positive number, so 8 minus negative 4 is 8 plus 4 is 12, and negative 3 minus 5 is negative 8. So we get 12 over negative 8, which simplifies to negative 3 halves when I divide the top and the bottom by 4, and I can also bring the negative sign in front. That's the slope. All right, we got to get the slope-intercept form of the equation of the line, however. There's a couple ways you can approach this. There's something called point-slope form, which people often write like this: y minus y1 equals m times x minus x1. Okay, and that's fine. It's based on the definition of the slope. I prefer just going ahead and adding y1 to both sides right away anyway, because this reminds me that when I think of y as a function of x here, I can see that m is the multiplier of the x. That's going to be the slope. I can also see that if I replace x with x1, I will get 0 right there, and I'll get y1 for the output of this function. So I prefer having it right like that right away. Go ahead and plug the slope in. M is negative 3 halves. X minus x1. x1 is 5. That'll be like this. And then plus y1. y1 is negative 4. Adding negative 4 is the same as subtracting 4. We're not done. We need to expand this. We need to simplify it to get it to slope-intercept form. Distribute the negative 3 halves through the parentheses. You'll get negative 3 halves x, and then negative 3 halves times negative 5. That's going to be positive 15 halves, which is 7.5, and then subtract 4, which is the same as subtracting 8 over 2. And so you'll get in the end here, y is negative 3 halves x. 15 halves minus 8 halves will be plus 7 halves. Or if you prefer, negative 1.5x plus 3.5. Okay, so there is the equation of this line in slope-intercept form. You can see the slope is -3/2 and the y-intercept is 3.5. If we wanted to make a quick graph to check things, you could say the 0.5, -4 is, say, right about here. 5, -4, and the point -3.8 might be right about here. -3.8. Connect those dots with a straight line and looks reasonable. -1/2, -1.5 for the slope and 3.5 for the intercept. Looks fairly reasonable. You'd want to draw it more carefully to be more sure. All right, on to part B. Find the slope-intercept form of the line passing through the point 2, 3, which is parallel to the line from part A. Parallel, it's going to have the same slope, -3/2, -1.5. Go ahead and right away use this form of the equation of the line. In this case, for part B, the same slope, -3/2, but now a different point, the point 2, 3. That's going to now play the role of x1, y1. So we get x minus 2, and then y1 would be 3 there. Now just expand and simplify to get the slope-intercept form. -3/2 x. -3/2 times -2 is going to be +3. Right there, yeah, the negative signs will cancel, plus another 3. 3 plus 3 is 6, so we get y equals -3/2 x plus 6. That will be the equation in slope-intercept form of the line that has the same slope but goes through a different point, the point 2, 3. Where is that point? It's somewhere around here, say. This line is parallel, and it's going to have an intercept, a y-intercept of 6 right about there. Okay. Part C. Find the slope-intercept form of the line passing through the point 2, 3 still, which is now perpendicular to the line from part A. Being perpendicular means that the slope is going to be what's called the negative reciprocal of the original slope. So this slope here is -3/2. Its negative reciprocal, the new slope, will be the negative of 1 over the original slope. The original slope was -3/2. The two negative signs will cancel. When I divide by the fraction, 3/2, it's the same as multiplying by 2/3. The slope that we're after here is going to be 2/3. So going back now to point slope form, right, like that again, replace m with +2/3 and replace x1 with 2, just like in part B, and x2 with 3, and then simplify. Y will be 2/3 x. Distribute this 2/3 through, we'll get -4/3, and then a +3. 3 is the same as 9/3. So we're going to get y equals 2/3 x. -4/3 plus 9/3 is going to be +5/3. That will be the slope-intercept form for the equation through this point 2, 3, right about there. That's perpendicular to both of these lines. It's going to look about like that, and the intercept is 5/3, 1.6 repeating. Looks reasonable. Problem number 3 is similar thematically to problem number 2. You're finding parallel and perpendicular lines. However, there are no numbers. It's all a bunch of letters. Don't panic. Take a breath. You can do this. The key thing to realize, first of all, is that the variables are x and y. All these other letters, the A, the C, the M, the B, they're all constants, okay? You could pretend they're particular numbers if that helps. Find equations. I'm going to go ahead and find the slope-intercept form of the equations, but I'll find other equations first. For the lines through the point A, C, you could pretend A is 7 and C is 10 if you like, that are parallel and perpendicular to this line, y equals mx+b. We're going to go ahead and assume m is non-zero to keep things simple. If m were 0, this would be a horizontal line, which would mean the line perpendicular would be vertical and its slope would be infinite. It can be done, but it's a little tricky, so we're not going to bother with that kind of thing. Okay? All right. Solve the problem. What about the parallel line? If I can spell parallel there. Parallel, it's going to have the same slope, just like before. That slope is m. That's a constant, not a variable. Write it down. But you don't write mx+b here. You need to make sure it goes through the point A, C. I need the point slope form. In the form that I showed you, go ahead and write x minus a in parentheses and then plus c. All right? It's got the right slope. m is still a multiplier of x. If you go ahead and distribute this out, you see that. And it goes to the right point. If you think of this as a function of x, and you plug x equals a into that function, you'll get a 0 right there. M times 0 plus c. 0 plus c is c. The output, the y value, will be c. This is the right thing. That's an answer. Maybe for emphasis, we might want to put these two terms in parentheses to emphasize that's the y-intercept. And maybe you feel like putting the c first since it's positive. Plus, and I'll put parentheses, c minus m times a. So m is the slope. And this quantity right there, that will be the y-intercept. Okay? There'll be your parallel line, ultimately, if you want it in slope-intercept form. What about a perpendicular line? Perpendicular. Just like in the previous problem, the slope is going to be the negative reciprocal. If I need m to be non-zero if I want the negative reciprocal. By the way, if m were 0, I guess we could solve that here very quickly. If m were 0, this was a horizontal line. The perpendicular line would be vertical. Its x-coordinate would be the same as the x-coordinate of this, and this equation would actually just be x equals a. So that's actually fairly simple. But we're assuming m is non-zero. So the slope that we're after here is the negative reciprocal of m, which is negative 1 over m. That'll be the slope of the perpendicular line. I wanted to go through the point AC again, so I need to do the same kind of thing here with parentheses, write in x minus a, and then add c. Then to simplify in slope-intercept form, distribute the negative 1 over m through the parentheses here. Negative 1 over m times negative a is positive a over m, then plus c. And then probably the most natural thing to do here to simplify a little bit more is to add these two expressions by getting a common denominator. C is the same as mc over m. And again, I'm assuming m is non-zero in all this. And then I can now add those fractions by adding their numerators. I can write plus a plus mc all over m. And maybe for emphasis, put that in parentheses to emphasize it's the y-intercept. And the slope, again, is negative 1 over m. And there's the equation of a line perpendicular to the original line. Number 4 is an applied word problem. The cost for commercial waste collection is $845 for 10 tons and $1,148 for 15 tons of waste. Again, we'll do this step by step. It's got numerous parts here. Part A, find a linear formula for the cost C in dollars of waste as a function, maybe I'll go ahead and use function notation as well, of the weight W in tons. That's what part A is. So I want the cost, C, to be a function of the weight W. C equals F of W. Okay? It's going to be a linear function. That's the assumption here. Is that reality? Well, it's the background assumption. You'd have to check into the way the waste collection does their business to see if it matches reality. It's certainly a natural thing to do, but you'd have to look into it to see if it matches reality. The slope is still going to need to be found. I've written delta y over delta x before. If I want to use these variables, it's delta c over delta w. It's always the change in the dependent variable divided by the change in the independent variable. Where are my points? Well, they are there, but got to be careful. The c and the w are switched around, you might say, from the way you'd think of them in terms of the function. In other words, when you think about this function, you'd want to think about the w coordinate first and the c coordinate second. So this data point right here corresponds to the point w comma c equals 10 comma 845. That's probably the trickiest part of this problem. And this one right there corresponds to w comma c equals 15 1148. You got to switch them around if you're thinking of c as a function of w. So now delta c is going to be change in the cost 1148 minus 845 divided by delta w, that's 15 minus 10. Go ahead and use my calculator here to make sure I don't make a mistake. 1148 minus 845 is 303, and that's going to get divided by 5. 60.6 is the slope. All right, I'll go ahead and use the decimal form of it. That'll get plugged in here. I'm using, once again, point slope form initially. 60.6 is the slope. The independent variable is w, not x. Use a w here. You can use either point. I didn't really emphasize that before. You can use either point when I write point slope form. I'll go ahead and use the first point. So w minus 10 and then plus 845. That is the formula for c as a function of w, but let's get it into the standard slope-intercept form. So I'll get 60.6w minus 60.6 times 10 is 606 plus 845. So ultimately we get c equals f of w equals 60.6w 845 minus 606. Can I do that in my head? That would be 200 and what? 239? Especially when you're doing a video, it might feel like, oh, I'm afraid I'm going to make a mistake in front of 1,000 people or something. Yeah, it looks like it's 239. Okay, didn't make a mistake. All right, so that looks like it's the cost C in dollars as a function of the waste, tons of waste in tons there. Okay, that's part A. Part B. What is the slope from part A? We already know the answer pretty quickly. Give units and interpret your answer in terms of the cost of weight collection. That's the more important thing to do here. So the answer for the slope, M, we already found, is 60.6. What are its units? Its units, since it's calculated as a ratio like this, are units for C per unit of W. Unit of cost per unit of waste. Units of cost are dollars, units of waste are tons. This is in dollars per ton. That's its units. What does this mean? It means for every extra ton that gets collected, it's going to cost 60.6 more dollars. For every extra ton collected, the cost will go up by $60.60. Okay? There's the interpretation right there in terms of waste collection. That's important to know. Part C. What is the vertical intercept of the line from part A? Give units and interpret your answer in terms of waste collection. It's right there. There's your C-intercept. That's your vertical intercept. W would be horizontal, C would be vertical. The vertical intercept, which is the C-intercept, is 239. What are its units? It's the same as the units for C. This would be dollars. $239. What is the interpretation of that? That's the value of C. That's the cost when the tons of waste is zero. When you replace W with zero, you get 239 here. This is the cost of waste collection when W is 0 tons. In other words, there's no waste. Does that make sense? Should you be charged when you don't have any waste? Well, if you've set up some sort of contract to have the waste collected, yet you don't have any waste, you still got to pay based on the contract. In this case, evidently $239. So yes, it is something that could happen in real life. Problems 5 and 6 are about proportionalities. Number 5 has two parts. Part A, if y is directly proportional to x and y equals 9 when x equals 4, find y when x equals 12. Let's go ahead and do that first. What does directly proportional mean? It means there's some constant, I like to call it k, though I could call it m because it would be a slope, such that y equals k times x. That's what it means for y to be directly proportional to x. As far as solving the rest of part A, just plug the numbers in first to solve for k based on these two data points, you might say, and then using that value of k, Solve for y when x is 12. All right, so we got these two data points. Y is 9 when x equals 4. In other words, the point 4, 9 would be on the graph of this. Replace y with 9 and x with 4. This allows you to solve for k. K is going to be 9/4. And then you can use that to solve for y when x is 12. K is 9/4. Multiply that by 12. The 4 and the 12 divide out to give you a 1 and a 3. And then you end up with 9 times 3 is 27. There's the answer, 27. There's actually another way that problem could be figured out. It's a property of direct proportionalities that when x increases by a certain factor, in this case by a factor of 3, and going from 4 to 12, 3 times 4 is 12, y also has to increase by the same factor. From 9 to 3 times 9 is 27. That would be another way to solve this problem without actually finding k. But in general, you might want to play it safe and find k. Part B. Here, y is inversely proportional to x. That means there's some constant of proportionality where y does not equal k times x, but y equals k divided by x. That's what inverse proportionality means. Once again, we can use the data points to ultimately solve the problem. Find k first, replace y with 4 and x, y with 9 and x with 4. Solve for k. K is going to be 9 times 4, which is 36. And then you can use that value of k to finish the problem. Y will be 36 over 12 when x has increased to 12. 36 over 12 simplifies to 3. This problem also can be solved in a different way without solving for k. Once again, x is increasing by a factor of 3 from 4 to 12. 3 times 4 is 12. To find the new value of y, you have to divide it by that factor instead of multiplying it. 9 divided by 3 is 3. Okay? So you can solve that problem without solving for k as well. As promised, problem 6 is also about proportionalities. Write formulas representing the function in each case. Part A, the average speed v for a trip over a fixed distance d is inversely proportional to the time of travel t. All letters here, you can handle it, just take a deep breath. The average speed v, ultimately we're going to think of as being a function of t. Think of d as fixed, okay? There's all letters here, but the way you think about them is important. The inverse proportionalities with respect to t, it's a fixed distance d. It could be 10 miles or 100 kilometers or whatever. I want to ultimately think of v as a function of t, but the d will still be in the formula. It's inversely proportional to the time of travel. There's some constant of proportionality. I'm initially going to call it k here, where v equals f of t equals k divided by t. And the question here is, what is k? You may know the equation distance equals rate times time. That's essentially what we've got here, except we divided both sides by the time. In other words, this is the same as rate equals distance divided by time. In other words, k has got to be the distance traveled. Okay, k has got to be d in fact. So you can write v equals f of t equals d over t ultimately. Okay? That's what we got for the answer to this part. Part B, the energy E, not giving units for these things, by the way, that's okay, we could give units, expended by a flying bird is proportional to the cube of the speed v. Is that true, you might wonder? I'm not sure, but saw this in a book, and so I'm assuming it's right. It's proportional to the cube. What's a cube? Well, of course, a geometric cube is like a box shape with all the sides have the same length. That is related to volumes, and that's why we call when we raise a quantity to the third power, we call it a cube. When you raise a quantity to a second power, you call it a square because it's related to areas of squares. So E is proportional to the cube of the speed. There's some constant of proportionality, k, where E is k times the cube of the speed, k times v cubed. We're not given any more information. We can't specify what k is. That's the answer right there for some constant k. All these quantities, by the way, are positive. D is positive, k is positive. That could be remarked as well. Sometimes constants and proportionalities, depending on the application, are negative, and that's worth knowing sometimes. Problem 7 is about domain and range. Find the domain and range of two functions that are related to each other. F of x equals x squared plus 5, and g of x is 1 over f of x, 1 over x squared plus 5. All right, what's a domain? A domain is the set of all possible inputs. Now, technically speaking, you can always decide what your domain is to some extent. But when you see problems like this, typically what you're after is the biggest possible domain, at least when you're not considering complex numbers. We're only considering real numbers when you're doing typical pre-calculus and calculus content. So for f of x, the domain of f, you can plug in any real number into that. No problem. You're not dividing by 0. You're not taking the square root of a negative number. We do want real number outputs. No problem. The domain is the entire real number system, the entire real line. Here's some fancy notation. An R that looks like that with two lines there, sometimes written in boldface in books, represents the set of all real numbers. You might say all decimals where any kind of decimal expansion is allowed, repeating or not. Repeating decimals are always represent rational numbers. The non-repeating decimals represent what we call irrational numbers. Put those together, you get the real numbers. You'll also see this set sometimes written in what's called interval notation. Minus infinity to infinity with parentheses around them. That represents all the numbers on the real number line. You could also use set builder notation, the set or collection of all x such that x is real. This vertical line means such that. And this funny looking thing right there means technically is an element of, though I like using the shorthand word in. X is in R. It's an element of the real number system. It is a real number. That's the whole thing's called set builder notation. Little bit of overkill here, but you'll see these kinds of things in different classes. Range is trickier. What's the range of f? Range is always trickier. It's the set of all outputs as the inputs range over the domain, and pun intended there with using the word range again. So you got to think about the graph of f of x. Okay, you could use your calculator, but that's not too difficult. Graph of x squared is a parabola with its vertex at the origin. By adding 5 to it, we shifted upward by 5 units. The graph is going to look like this. It's the graph of f of x, and it's going to have a low point at when x equals 0. Y will be 5. That'll be its minimum value. What are all the possible outputs that you can get as you plug in different numbers into this function? They are all the numbers greater than or equal to 5. All the numbers up there. Most commonly, you'd probably write that in interval notation. And you'd write it like this, using a square bracket for the 5, because 5 is a possible output. When x equals 0, the output will be 5. But with the infinities, infinity is not a number, by the way. When you write these things, don't think that that means infinity is a number in a calculus class. It just means we're going out to infinity. You might say we're going out forever and ever. The outputs go up forever and ever here. In set builder notation, it's probably more natural to use the letter y because we're thinking of this as being along a y-axis here, but you don't have to use the letter y. Set of all y such that y is greater than or equal to 5. By the way, if 5 were not in the range, we'd want to use parentheses there instead of a square bracket. But 5 is in the range. How about g of x? Domain of g of x, or just g. Well, you'd have to be very careful sometimes about dividing by 0. However, x squared plus 5, if x is a real number, is never going to be 0. So you're never dividing by 0 here. The domain of G is also the set of all real numbers. Okay, you can plot this over the entire real number line. You're never dividing by 0. Range is still tricky, though. Range of G. What are all the possible outputs? Once again, a graph could help. Can I do it without technology? Yeah, I think I can here. G is the reciprocal of f. I'm taking all the outputs, the y values here, and doing 1 over them. The low value of f, 5, becomes the high value of G, 1/5. Though I'm using a different scale here. 1/5 is going to be the highest possible value of G, and it's going to go down on either side from there. As x gets further and further away from 0 in either direction, the outputs of f of x get bigger, 10, then 100, then 1,000, then 1,000,000. So the outputs of G get smaller, 1 over 10, 1 over 1,000, 1 over 1,000,000. They get smaller and smaller, though they never equal 0. The x-axis here is what you call a horizontal asymptote. This function will approach 0. Its limit will be 0. We talk about limits later as x goes forever to the right or forever to the left, but it will never equal 0. It can equal 1/5 though. So in interval notation, we go from 0 to 1/5, not including 0, but including 1/5. That will be the range of G. Set of all y values such that y is strictly greater than 0, 0 is strictly less than y, and y is less than or equal to 1/5. That'll be the range of G. The next couple questions are pretty conceptual, symbols and graphs, but no formulas. Number 8 says, the value of a car, V equals F of A, in thousands of dollars, so V is in thousands of dollars, is a function of the age A of the car in years. Okay, keep your wits about you. V and A are variables. V is the dependent variable, A is the independent variable, F is a function. V is in thousands of dollars, A is in years. Keep that kind of thing straight. That's essential for part A. Interpret the statement F of 4 equals 15. F of 4 equals 15. This is an A value, and this is a V value. What does this mean? It means when the age is 4 years, the value is $15,000. When the age is 4 years, this is the interpretation. 4 years, the value of the car is, don't just say 15, give units, $15,000. Okay? Got to understand function notation. Part B, sketch a possible graph of V against A. V is a function of A. It would be traditional to put A on the horizontal axis and V in the vertical axis. And age can't be negative, so really I only need the part to the right of the V axis here. At age 0, the car has some value. And if you know about something called depreciation, the value's got to go down over time. As the car gets older, the value goes down. This graph has to be what's called a decreasing function. Is it a straight line? Maybe. I mean, that would be simple to assume it's a straight line, and maybe for purposes of counting, you could assume that. But in reality, in terms of what its true value is, and that's determined by supply and demand, what are people willing to pay for it, it's probably not a straight line. It is a decreasing function. I would argue it's shaped like that probably. It's what's called concave up. It kind of looks like part of a smile. Technically speaking, it means the slope of the graph gets larger and larger. The slope is negative here, but it's getting closer and closer to 0. Is f increasing or decreasing? It's decreasing. So this is V equals F of A. This is a decreasing function for most cars, at least. As long as it's not some sort of classic car. It's decreasing. Explain. because of depreciation. You know, people want, in general, new cars. Depreciation. The value goes down over time. People want new cars, so they're less willing to pay for old cars. Part C. Explain the significance of the vertical and horizontal intercepts, if any, in terms of the value of the car. Well, the vertical intercept, where it crosses the v-axis, is its value when a is 0. There definitely would be a vertical intercept. V-intercept, which is the vertical intercept, is the value of the function when a is 0. That's the value of the car when it is new. Its age is 0 years. Sorry that I didn't have that in the camera there. Value of the car in $1,000. When it's new, A equals 0 years. Okay? How about the horizontal intercept? I would argue technically there's no horizontal intercept. Okay? Technically speaking, even if your car is 30 years old, it's got a tiny bit of value as long as it's running. I mean, well, even if it's not running, it's got some junk value. If it did have a horizontal intercept, an A-intercept in this case, that would be the age at which its value is 0. You could write that down. A-intercept, if any, is the age at which the value is 0. $0 or $0,000 if you want to emphasize the 1,000 again. I would argue again that there is no A-intercept here. You could argue that there is no A-intercept. There is no age at which the value is 0. The A-axis is acting kind of like a horizontal asymptote. Is it really a horizontal asymptote? Actually, not necessarily. It could be approaching some positive number like $100, which would be $0.1,000 or something. But that's what I would say. If I were grading this, I would say either answer is okay. Number 9 is also conceptual. Plot graphs for the following story. As I drove down the freeway this afternoon, at first the traffic was fast, and I'm congested, moving fast. Then it slowed down to bumper, traffic jam, through the road construction. We're going slow. After which the traffic flow went back to normal until I got off the freeway. We're plotting graphs for this story. 2 graphs. Part A, driving speed against time on the freeway. Okay, and part B you can see is driving distance driven against time on the freeway. Just a graph here. Time on the freeway is the horizontal axis. It's against time. The speed is on the vertical axis. Okay, this is a pretty important conceptual problem for understanding calculus. Going fast at first, the speed is high. Then we slow down through the road construction. The speed is low. Then we speed up again after we're through the road construction. So the speed graph has to be something like this. Okay, now I'm making it smooth. No corners in the graph, it's continuous, no breaks in the graph. Is that true? Probably. I mean, it might be more extreme than what you see here. Might be a big slowdown, a fast slowdown, then a fast speed up or something. But this is the basic idea. Part B, graph distance driven against time. So I'm going to go ahead and make this graph, and the most important thing is these graphs are actually related to each other. When the speed is high, the distance graph changes rapidly. How far I've gone changes rapidly. If you go really fast, you're traveling a lot of distance in a short amount of time. The slope, you might say, is very large. So initially, the slope is going to be large here, going up fast. Distance traveled at time 0 is 0, so it's going to go through the origin here. But then when you slow down, going through the construction, you're not moving very fast. The distance is not changing very rapidly. The graph is still going to go up. It's still going to be increasing, but the slope is going to be smaller when I'm in this time region where the speed is smaller. And then it speeds up again, so the distance graph gets bigger in slope again. These graphs are related. This graph, the speed graph, is telling you the slope of the distance graph. Slope, steepness is high here, just like the speed is high in value here. Slope is still positive but low in here, just like the value is positive but low here. And then over here, the slope is back to high again, just like the output, the value is high. Look at the outputs, the second coordinates here, and the slopes there. The speed in calculus is called the derivative of the distance traveled. That's our first calculus concept. The last problem is kind of challenging. Abstract problem-solving kind of thing. We've got graphs here. Consider the functions graphed in this figure. The goal is to find the coordinates of the point C in terms of this unspecified quantity B. Again, don't panic. X and Y are the variables. B is evidently a constant. Though it'd be interesting to think about how is C affected by that constant changing, which sounds oxymoronic. How can constants change? Well, they can change if you want them to change, okay? You can think about what happens for different values of B. In fact, that's very interesting sometimes. All right, what in the world are we going to do? Find the coordinates of the point C in terms of B. I don't know what those coordinates are. Maybe I should give them names at first. A comma C? I could. However, that's a big C, there's a little c. However, I've got graphs here. C is both on this line and this parabola here, y equals x squared. Capital C, I mean, the point. Therefore, the coordinates of capital C, little c, have to satisfy that equation. I can say, since C, this is capital C here, C is on y equals x squared, that implies that little c equals a squared. So in fact, that means you can go ahead and replace the coordinates here with a comma a squared. Okay, that seems like it might be helpful. What else should we do? Well, the capital C, the point is also on this line, as well as these 2 points being on that line. This point is the point 1, 1. This is the unspecified point 0b. Maybe I should find the equation of that line and use the fact that capital C, that point, is on that line. That sounds like it might be a good idea. It might not be clear for sure if it's going to help us finish the problem. This is what happens in problem solving. You just got to try things sometimes, and it's more information. It's got to be helpful in some way. What's the slope of this line? Delta y over delta x. Here's our 2 points. Change in y is going to be 1 minus b. Second coordinates, 1 minus b. Change in x is going to be 1 minus 0. Of course, 1 minus 0 is 1, so this simplifies to 1 minus b. 1 minus b is the slope of that line. Okay, that's going to be a negative slope, as in this picture, when b is bigger than 1. It'd be a positive slope, actually, if b was less than 1, if this point here were down there, which it could be. What's the equation of the line here? Go back to our old friend point-slope form. Y equals the slope, 1 minus b, times x minus the first coordinate of the point on the graph, and then plus the second coordinate of the point. Which point should I use, 0b or 1, 1? Technically, it doesn't matter, but maybe it'd be, actually, it'd be simpler to use, I wouldn't even have to write this form of it if I use this point here, 0b, excuse me, this 0. That's what I meant to put there. 0 in there, b out there. Yeah, I didn't even need to write x minus 0 because it's just x. 1 minus b, x plus b is what this simplifies to. And if you simplify it, yeah, I could have written that without thinking about point slope is what I'm trying to say here. So there's the equation of the line in terms of b. I know the point capital C, whose coordinates are a comma a squared, has to satisfy this equation. My goal is to, again, figure out what these are in terms of b. That's going to give me a relationship between a and b. Maybe I can solve that for a in terms of b. Yeah, that's what I want to do here. C is on here. Capital C is on here. So its coordinates, a comma a squared, have to satisfy that when x is a and y is a squared. Replace y with a squared. Replace x with a. My goal is to figure out the coordinates in terms of b, so I want to solve this equation for a in terms of b. That'll do it. It's a quadratic equation in a with no numbers except the 1. Usually, you know, when you have quadratic equations, well, you try to get 0 on one side and then you try to factor them. That doesn't really seem like it's going to be possible here. Here's how to get 0 on one side. I subtracted b from both sides. I also subtracted this from both sides, which is the same as adding that. Subtracting 1 minus b in parentheses times a is the same as adding b minus 1 in parentheses times a. Can't really factor that, it seems. So what do I do? Quadratic formula. Quadratic formula. You know, in its usual form, you write your quadratic as ax squared plus bx plus c equals 0. And you say x is negative b plus or minus square root of b squared minus 4ac all over 2a. By the way, there's a calculus lesson video. Was it lesson 1.3, I think, where I sing the quadratic formula if you want to hear me sing. It's a little confusing here because you got a's and b's here and a's and b's there. And they're playing different roles, really. When I look at this equation, I want to treat the a as the x down here, because that's the unknown. I want to solve for a. So I've got to treat it like the x. The coefficients corresponding to the a, the b, and the c down here are 1, b minus 1, and negative b. Those are the coefficients playing the role that the little a, little b, little c do down there. So you got to be really careful. It's pretty tricky. So applying the quadratic formula to solve for a, negative b means negative of this thing, which means 1 minus b, if I negate that, plus or minus square root of this thing squared, that's playing the role of b, it's got to be squared, b minus 1 squared, minus 4, what's playing the role of the a there, it's a 1 times 1. What's playing the role of the c there, it's a negative b. All over 2a, 2 times 1. Ugh, it doesn't look so simple. Keep going. Don't give up. Simplify, expand that out. I'm foiling in my head here. b minus 1 quantity squared is b squared minus 2b plus 1. I foiled in my head. You need to look that up if you're forgetting. Two negatives there make a plus. Plus 4b over 2. Don't give up. Simplify some more. Negative 2b plus 4b is positive 2b. Are we done? No, this can be simplified some more. This thing can be factored as b plus 1 quantity squared. Now that might not be obvious at all to you, But it is true. It's something to be able to recognize. Just like this thing in here was b minus 1 quantity squared. So this thing here is b plus 1 quantity squared. Now technically the square root of something squared, let me write a z squared or something, is technically the absolute value of that number, not the number itself. It does equal the number itself when the number is positive, but it actually equals the opposite of the number if the number is negative. And if z is negative, then negative z is positive. So yes, you always do get a non-negative output for this expression. So technically, the square root of this thing squared is the absolute value of b plus 1. But hey, b is bigger than 0 here. At least I'm assuming that. So b plus 1 is positive. I really don't need the absolute value signs. B is positive, so 1 plus b, or b plus 1, is also positive. And so I can say this is that a is 1 minus b plus or minus square root of b plus 1 quantity squared is b plus 1 over 2. Giving me two possible answers for a. If I take the plus sign, the minus b and plus b cancel. 1 plus 1 is 2. 2 over 2 is 1. A could be 1. Or if I take the minus sign, the 1's cancel. 1 minus 1. And with the b's, I get negative b minus b is negative 2b. Negative 2b over 2 is negative b. Hey, when a is 1, that's really that point. The one we must be after is negative b. So the final answer is that the coordinates of c, which are a comma a squared, are negative b. Negative b quantity squared is just b squared. There's how the coordinates of c depend on b, and that does solve the problem. I found how the coordinates depend on b. Thanks for watching the first video in this problem series.